Usually, professional CAD software needs beefy computers, or at least a decent hardware to run most of its features. But in recent years, cloud-based tools have become very popular and are trying to provide almost the same feature as their offline counterparts. You would have noticed this trend in mechanical CAD application, where cloud-based applications like Fusion 360 and Onshape are gaining a very large user base. Similarly, in the field of electronics CAD, we have EasyEDA, Flux.ai, and Fusion 360. Which makes the application very accessible on older systems and also provides a collaborative platform to work as a team. So to take advantage of these cloud softwares, we are starting a new series where we'll learn how to use EasyEDA while building a PCB for a battery management circuit. Before we leap into the fun stuff, let's talk a little about EasyEDA and how things work here. EasyEDA comes in 3 different variants. We can either use a standard, pro, or the offline client version. If you are just getting started with PCB development, I would highly recommend using the standard version, which is very easy and simple to learn. To start, no installations are needed. Just hop on over to easyeda.com and register a new account. Once you're in, head to the home page and click on EasyEDA Designer, and on the pop-up, select the standard edition. This will open the EasyEDA online editor with a very simple user interface. Here it seems like we have little to no option. So first let's start with creating a new project. To do that, click on this icon here. On the pop-up, give a project title and some detail about the project, and then hit on Save. This will unlock all the features that EasyEDA has to offer, along with creating a new sheet where we'll do the schematic capture. Since this is going to be a second home now, let's quickly take a look at the UI and how things work in EasyEDA. For navigation like zoom in and zoom out, use the scroll wheel. And to pan across the document, just middle click and drag. Finally, to fit the document on window, just click on this Fit to Window icon. Now on the left, we have the project panel, which shows all the project files and folders that we just created. Then below that, we have the design manager to keep track of components and nets that will be adding to the circuit. Then the commonly used list of components, followed by a full-fledged online library with thousands of parts. Now for the tools, we can use these floating windows. Wiring tools should give you access to tools like bus, net labels, and other tools that's related to schematic design. Similarly, the drawing floating window should give you tools like the document editor and various graphic tools that make your circuit look pretty. Finally, we have the object properties panel, which will give you more details about various objects like symbols and graphic elements that will be placed on the drawing sheet. Lithium batteries have become very popular in recent years. These batteries are perfect for storing higher energy level with a very small footprint. But with this immense power, there is an element of risk lurking. Now that I got your attention, we are not going to build a battery management system for EVs, which is overkill for beginners, and building that in EasyEDA would be quite challenging and very difficult. So instead, we are going to look into how to build a battery management circuit for consumer electronics like MP3 players, wireless devices, and other electronic gadgets. Consumer electronics oversimplify the working of lithium batteries for user experience. You see, they just don't follow a linear progression from 0 to 100 and back to 0. Instead, when the battery is fully charged, it boasts a voltage of 4.2 volts, and when it is discharged, it drops the voltage to around 2.5 to 2.7 volts. Now, why do these voltage values matter? Lithium-ion or lithium polymer batteries have a higher energy density, and this voltage level tells us the energy level of the battery. So whenever we are planning to use one of these batteries in the circuit, we need to make sure that the battery doesn't overcharge above 4.2 volts or over-discharge below 2.5 volts. In case if it goes over 4.2 volts, the battery temperature might shoot up and possibly explode at some point. And if it's below 2.5 volts, the battery will completely drain and lose its ability to charge again. So it's very crucial to monitor this while charging and discharging lithium batteries. Along with monitoring these values, we should also make sure the battery doesn't short circuit or pull current greater than the rated current, because this could increase the temperature of the battery significantly and reduce its lifetime. With this simple understanding of lithium batteries, we can come up with few parameters for a BMS design. For few applications, this should be sufficient. We can connect the circuit directly to the output of the BMS, considering we only have to add a voltage regulator and the circuit needs only 3.3 volts. But this method is very inefficient, and some applications need voltages up to 5 volts to operate. In that case, we need to have a buck or a boost converter for voltage conversion to use the battery more efficiently. There is a lot more to battery management apart from this, like having a fuse, monitoring individual cells in series, current sensing, temperature sensing, and auto cutoff after charging. We don't have to rush into all these features at once and look into these in the future videos. Here we can build individual circuit for each of the parameter using discrete parts, but it's very inefficient, time consuming and expensive to do so. As an alternative, we can quickly rig this up using a TP4056 module, which provides a required battery protection and a MT3608 boost converter to convert the battery voltage from 3.7 volt to 5 volts. It works, but it seems like a lot of part once we break down the components in these modules. So after some research, I found this part, IP5306, which has all the functionality that we need. At the same time, it's easy to integrate and has an inbuilt battery level indicator. I did find more alternative components, but this IC was significantly cheaper, easier and simpler to use. If we pull up the datasheet for this particular IC, we can see all the protection it offers, along with some more features that are more advanced than TP4056 and the parameters that we discussed. Sorry to interrupt, just a side note. If you enjoyed this video so far, make sure to hit the subscribe and the like button, which will really help us make more similar YouTube videos. We have the component selected now, but how do we figure out the circuit around this IC? And what additional components do we need? To get answers to these questions, jump back into the datasheet and search for the application diagram, which should give us the minimal setup that we need to use the IP5306. Since we know what components and connection we need for the IC, let's dive deep into EasyEDA to build this. Open the sheet that we created in the previous video. Here let's start with adding the main IC. So go to the library here and search for the part we need, IP5306. You can see it directly pulls up the symbol from LCSC along with its cost and stock availability, which is super handy if you decide to import the parts or assemble your PCB within JLC PCB. Anyway, now to add the part to the sheet, just double click on the part and then left click to place it on the sheet. And to exit the component placement tool, just hit escape on the keyboard. This is the only uncommon component that we had to find for the circuit. The rest of them like capacitors, resistors and inductors should be easily available in the common library. Just click on the component that we need and click on the schematic sheet. If you like to rotate the component, you can just press the letter R. And you can press the escape key to come out of the component placement tool. Now with that, I'll quickly add the rest of the components in appropriate places according to the application diagram for easier connection. With this, we can move on to connecting the components together. First, select the wire tool from the wiring tool window. Or you can just use the shortcut W. Then select the pins with a left click and connect to the next pin that you'd like to connect. We can also change the direction of the net by just doing a left click and also stop the net with a right click whenever necessary. With that information, I'll quickly build rest of the circuit using the application schematic as a reference. Here you can see I'm ignoring the key feature, so I have a pin hanging. This could confuse both us and the EDA when the circuit gets complicated. So I'll use the no connection flag from the floating window and place it here. With this, we can save the file with Ctrl S. Now go to the design manager and see how many components and nets we have added to the circuit. We can understand most of the things in the components folder, but it's very complicated to understand what's happening with the nets. So to clean this up, we can use the net label tool and give names to these nets. Once you have given the names to the net, you can hit the small refresh icon in the design manager to see the changes. This net label not only reduces confusion, but also it helps in avoiding overlapping nets by separating them into different modules. There are more tools in the floating window, but few of the tools are just duplicates, like these power nets, which are also available directly from common library. Apart from this, we have the voltage probe tool, which is used for simulation, group tool for grouping components together, and finally, bus and bus entry tool for more complex circuits. Maybe in a future video, we'll dive deeper into these tools for better understanding. Next, let's add the value to the component. Just select the component you need and double click on the value. And on the pop-up, we can enter the value that fits our circuit. I'll make sure I do this for all the components in the schematic. Anyway, this completes the electrical part of the schematic. But we need more information and details on this documentation if you're planning to share it with a team or make it open source. To do that, we need to make the circuit look nicer by using the drawing tools. Let's start with editing the document size. Once that's set, I'll change the value on the document sheet by just double clicking on the item and renaming them. And to add a border to the circuit, we can either use the line tool or the rectangular tool. Just select the tool, click on the area and start drawing. Once it looks good, just do a right click. We can use more drawing tools and personalize the schematics much better. And most of the tools here behave just like they should, according to the icons they have. like Bezier curves, arcs, arrows, text, drawings, polygons, circle, and pi. But I'm not going to use any of these except the text tool, since all this comes under personal preference. Instead, we'll just focus on adding a logo to the schematic using this image tool. Finally, these two bottom tools can be used to move the circuit or set the origin of the document, which is pretty rarely done. Now, if you like to customize more, each of these tools and elements has its own properties that you can play with to highly customize the circuit as you like. We can remove the grids, change the color of the nets, change the text color, and much more. There are three ways to create symbol within EasyEDA: manual, symbol wizard, and finally, datasheet extraction. First, we'll start with the manual method to better understand all the tools and workflow for creating a symbol, and then move on to the other methods to reduce the time and the effort required. To start, go to Files, New, and click on Symbol, which will create a new symbol sheet. Here, the tools are very similar to the ones that we are used to in the schematic editor's drawing tools, except for the additional pin tool for adding the pins to the components. Using these tools, we can build any type of symbols we need, including ICs, transformers, and resistors. But to keep things simple, let's start with replicating the IP5306 IC. Since we are going to build an IC, let's start with drawing a rectangle using the rectangular tool. Next, let's add the pins using the pin tool. Currently the pin says 3, but usually the IC numbering starts with 1. So to change this value, we need to go to the object panel on the right and change the name and the pin number as per the datasheet. For spice property, we don't have to worry much since it's used in simulation and we are not going to do any of those. As for the next two settings, set them to S to display both the name and the number of the pin, so it's visible in the schematic sheet. The pin length will determine the size of the pin. For now, let's keep this at a default 20. And here in the pin placement, if you prefer accuracy over simplicity, you can simply use the X and Y coordinates to directly change the position of the pin instead of dragging around it with a cursor. The next few options are for personalization, where we can change the pin color, the text color, but again, I prefer the default settings of the EasyEDA. Then the next few options can help in setting the electrical properties of the pins, like mentioning the inverted signal pin with a dot property or mentioning the clock signal of the IC. In our case, IP5306 won't need both of these options. There are some situations where we would like to have the pins but not use them. In such case, we can use this property to hide and unhide the pins. Currently, it doesn't seem to do much, but the effect will be on the schematic editor when we import this symbol. So just for a demo, I'll keep this at no and later we'll come back to change this value. Then we have the electrical properties, which will help in defining the electrical properties of the pin. In this case, we'll set the V in pin to power input, as this pin carries the power that goes into the IC to charge the battery and also power the IC according to the datasheet. Finally, there are few more options, but they are purely for aesthetics, so I'll leave them at default. And this completes the setup for the first pin. Now, to add the second pin, we can follow the same process. To make entering values and the pin number a tiny bit easier, we can just double click on a value and change it directly. However, we still have to use the properties panel for more options. Anyway, I think this should give you an overall idea on how to create pins for your symbol in EasyEDA. So I'll quickly add few more pins and modify them as required. This symbol looks good, so let's save it by using the shortcut Ctrl S and giving it a name. Let's call it IP5306 manual. You can also provide other information like supplier details, supplier part number, manufacturer details, link to the datasheet, and more. But for the sake of simplicity, I'll stick with the name and the description. Once that's done, hit save. Since the symbol was created within this project, we would instinctively expect it to be under this folder. But by default, this symbol will be stored in a global workspace, which can be accessed in all your projects. Now to check if it's actually located in the global library, go to the library and make sure the search engine type is set to EasyEDA and the class is set to workspace. Here we can see the symbol we created with the name IP5306 manual. Let's import this into the schematic and see how it looks. The first pin is missing. Oh yeah, that's because we set the pin show property to no. I'll quickly go back to the symbol editor and fix the property to S and save the file. The symbol is not updated yet. So to reflect the updated symbol, we need to right click and select the option Update from Library. This should update the symbol to the latest version. I know you would have noticed this by now. This custom symbol is not as visually appealing as the ones we got from the LCSC library. But of course, we can put more effort into making the symbol manually, so it looks very similar to the one from the supplier. But there is an easier way to do it. So let's start with creating another symbol. Here, instead of drawing the symbol from scratch, click on the symbol wizard icon on the toolbar, which should give us a pop-up wizard to create a custom symbol just by entering the pin configuration we need. By default, it's set to 12 pins, but we can change it to By default, it's set to 12 pins, but we can change it to a custom value by adding the pin name in order from the datasheet. When you click OK, it should auto-generate a symbol. This looks really good, but I'll just move these pins to the left so it looks exactly like the part from the pre-existing library. You can see this does a phenomenal job of creating a symbol, but we still need to manually adjust the pin properties or any other information that we like to change. But I hope you know how that process goes, so I'll quickly save the symbol and import it into our schematic. You can see this is very similar to the ones from the existing library, and we need to have the ground pen colored differently for easier understanding. And did you notice this was way faster than the previous method? How about I show you an even faster and more efficient way of creating a symbol? Let's start with creating a new symbol. Here, let's ignore both the manual method and the wizard technique. Instead, click on the datasheet extraction icon on the top menu bar. This should bring up a pop-up that will generate a symbol just from the datasheet image, which is super cool when you consider manually building a 50-pin IC. This pop-up is pretty simple to use. Just select the type of IC you need and import the datasheet image. Here I'm just pasting a snippet I captured from the datasheet. That doesn't look right. You might face this issue if you use a color image or a low resolution image. But it's pretty easy to fix. Just paste a better quality image with clearer text, which will fix the issue and autofill the complete pinout names for the IC. Once we are sure about the pin names and numbers, click on Next Step. Here we can select the pin designator and name of the symbol and click on OK. You can see that this created the part much faster than the previous two method without needing for any manual modification. But this method is not guaranteed to work with all the components or all the data sheets, although it works for most of the ICs. Now let's save the symbol and import it into our schematic. You can see we successfully created a symbol for EasyEDA with very little effort. But this symbol is just for representation and doesn't say much about how the physical component is placed on the PCB. If you're not sure what a footprint is, we'll drop a link in the description that will talk in more detail about footprints and why we are using them. Anyway, first let's start by figuring out the default footprints assigned by EasyEDA for these symbols. This will help us understand the shape and the size of the component along with its placement on a PCB. To do this, navigate to Tools and click on Footprint Manager or the shortcut Alt+F. In the pop-up, we'll see all the components used in the schematic along with their default footprints. And if you look close enough, most of the components here are based on 0603 package, which is incredibly small. But let's not break our heads with package numbers. Let's first try to understand how the footprint manager works and how we can utilize it to make the PCB development process much easier. Maybe in a different video we'll discuss more in detail about how the component packages are named and how to select a suitable one. On the left pane, we have a list of all the components used in the schematic editor. The top and the bottom pane illustrate how the symbol and the footprints are linked. Finally, the rightmost pane provides option to search for footprints within EasyEDA or footprints contributed by other users. To assign a footprint to a symbol, simply select the component and double-click on the desired footprint. It's that simple. But what if you want to create a custom footprint and use it? Well, that's easy too. Close the current window and navigate to File, New, Footprint. This will open a new tab with tools for building a custom footprint. If you're a beginner, I recommend watching our PCB Stackup video before using these tools. It provides detailed information about PCB manufacturing and why we design footprints or PCBs in certain ways. The first step in building any footprint is to check the datasheet and understand the type of component package we'll be using, along with its dimension and shape. In this case, if I open the IP5306 IC datasheet, the first page reveals that the IC is based on ESOP8L package. A quick Google search will lead us to the IC package wiki, which explains the difference between SOP and other available IC packages. We always encourage you to dig deeper to better understand why these packages are named this way. However, these values are not standardized across manufacturers. Therefore, I always recommend checking the datasheet instead of blindly selecting a footprint for your IC. Now, returning to the datasheet and scrolling down, we'll find the package dimension suitable for your IC. But remember, this is the dimension of the IC and not the dimension of the footprint. Not all the datasheet provide the dimension for the footprint. So we have to slightly modify this dimension to make a good footprint that has enough space to solder as well as place the component. I know there's a lot of information on the datasheet, but we only need to focus on a few details to build a footprint. As a starting point to build a footprint, we can always start with building a pad, where the components will be soldered and then build rest of the footprint. We need to know the component's lead dimension, and in this particular datasheet, the lead dimension is separately marked as section B, with the dimensions B and C. And to find this particular value, we have to scroll down a bit to find the value for B within this table. There are two values for B, because these represents the minimum and maximum variation in the size of the lead during manufacturing. As I told you before, this is the component dimension and not the footprint dimension. If we strictly stick to these values, we might end up with insufficient space for soldering. So as a rule of thumb, we can multiply the maximum value by 1.5 to get the pad dimension. With this information, let's return to the footprint editor. To create the pad, use the pad tool and place the pad at the center of the document. This is crucial because all the measurement will be relative to the center of the document as we work through the footprint. In the object panel, you can adjust the parameter of the pad as needed for our footprint. So let's start with the layer. Since this is going to be an assembly component, set the layer to top layer only. This ensures that the pad will only reside on the top layer and won't affect any other layer of the footprint. Next, set the number to 1, as this will be our first pin. Then select the shape to match the component lead. In this case, I'll change the shape to rectangle. And finally, here we can enter the width multiplied by 1.5 that we got from the table. To determine the height of the pad, return to the datasheet and check how long the pads need to be. This is marked as L in the datasheet. Multiply this value by 1.5 and enter the result in the object panel. Once we have one pad, we can quickly replicate this for the rest of the pads by copying and pasting them at a distance E marked on the datasheet. In our case, it's 1.27 mm. Here we don't need to multiply that value by 1.5 as these measurements are taken from the center of the lead. To ensure the accuracy of the placement, you can always use the object panel to set the precise distance between the leads. Now we have successfully built 4 pads on one side. Now we just need to replicate this on the other side as well. To determine the y-axis distance, return to the datasheet and look at the capital E value, which indicates the distance between the leads vertically. I will reduce the E value slightly, at least by half the L value, because EasyEDA calculates the distance from the center of the pad. This completes the 8 pads needed for the footprint. There is just one final ground pad left to complete. To determine this value, return to the datasheet and use the E2 and D value to create the pad. Also ensure the pad is centered. Once the footprint is done, I usually use the measurement tool to double check the footprint dimension with the datasheet, and I highly recommend you do the same. Once you are happy with the footprint, go to the pads and number them accordingly. We can stop the footprint at this point. But to make the placement of the component during assembly easier, we can use the silk layer to draw the outline of the component. Also, we can draw a small notch using the circle tool near the pad 1 to indicate the first pin. This process of silk layering is just for aesthetics and does not play any major role in electrical properties of the PCB, so it's up to you to design it however you like. Anyway, once you're happy with the footprint, you can save this custom footprint and give it a name. Just like the symbol editor, the footprint is saved globally and is not visible under the project folder. To access that, we need to go back to the schematic editor and use the footprint assignment window. You don't have to keep up with the following steps. I just want to show the difference between custom footprint we built and the footprint that was default within EasyEDA. As you can see, they look very similar, but with slight variation in the size of the pad because we took the multiplication factor 1.5 arbitrarily. and also because the silk layer looks much better with the knots on the default footprint. In our last video, we saw how to make custom footprints and assign them to the symbols within the schematic editor. Today, we are taking it a step further. We'll transform our schematic into a fully functional printed circuit board that is ready for manufacturing. If you have been following this series for quite some time, you might have noticed some changes in the circuit. Let's start by walking through some of the modifications I have made behind the scenes. For the input, I have included a USB-C circuit, offering a more convenient way to charge the battery compared to a regular header pin. Additionally, I have added a key switch and a LED to trigger the IC and serve as a flashlight respectively. Lastly, I have tweaked the output pins for easier placement on the PCB layout. These modifications are necessary, so I even built a version with our previous circuit, but the PCB looks too simple and impractical for many applications that I had in mind. The TP4056 is one of the most popular charging modules that's available in the market, so I thought it would be fantastic to create a version 2 of the famous TP4056 charging module. It's not something new, many have done it. However, I made sure this works as a drop-in replacement for the TP4056 with the exact size and dimension while retaining all the features of IP5306. If you prefer not to add this circuit manually, I'll provide a link in the description where you can download the schematic file. Alternatively, feel free to build the PCB with an existing circuit without any modification. First, let's start with the common mistakes beginners make when using EasyEDA. Creating a new PCB layout file directly from the file menu. Although it works, it doesn't automatically import all the components and the connection to the PCB editor, making the PCB design messy and challenging to work with. That's why we build the schematic first and then transfer the connection to our PCB layout. To do this in the EasyEDA, navigate the schematic editor and select Convert Schematic to PCB. This action will create a new PCB layout file in a tab and prompt you to enter your new PCB's dimension. Most options in this pop-up are self-explanatory. Set the units to mm, number of copper layers to 2, board outline to rectangular, and then start X and start Y to 0, which positions the PCB outline at the center of the document. Finally, enter your desired width and height for your PCB dimension. Since we are trying to recreate version 2 of the TP4056 module, we'll use its dimension, that is 27 mm in width and 17 mm in height. Once the values are entered, just hit apply. You'll see an outline for your PCB with your specified dimension and all the components and connection from your schematic editor. Anyway, let's start with the placement of the components onto the PCB. First, always start with the bigger component or the main component and then work yourself down to the smaller ones. To move the component, click and drag it to the desired location on your PCB. In any case, if you want to change the orientation of the component, just use the shortcut R. I'll start with positioning the USB-C on the left side of the PCB for easier access. If you're finding the placement of the component a little difficult, it could be the grid's close interval snapping. You can adjust this value on the object pane in the left. Let's set this value to 0.5 mm. Now you'll notice a difference in how the components snap to the PCB, allowing for more precise placement. Alternatively, you can just select the component and directly adjust its X and Y location in the object pane. For instance, I'm entering specific value here to center the USB-C symmetrically on the PCB. Next, let's bring in the IP5306 IC. The silk layer might obstruct our view at this point. You can just turn it off now and switch it back on later. However, since we need to fit as many components as possible within this space, I'm going to select the silk layer text and delete it. Now let's bring in the larger components like the inductors and the LEDs. If you're unsure about their placement, you can always refer back to the schematic that we did for reference. Next, let's position the input and output jumpers as precisely as possible to mirror the TP4056 IC. It seems we run into a bit of a snag here. All the components won't fit within this PCB. We might need to slightly increase the PCB size. To do this, let's delete the existing PCB outline and create a new one. Go to Tools, click on Set Board Outline and increase both the width and the height by 1 mm to 28 mm and 18 mm, then hit Apply. Now we can move around the components and adjust them until everything is packed tightly. While doing this, just remember one major point. Input pins, USB-C and output pins need to be in specific spots with certain dimension because we are replicating the TP4056 module. So use the measure tool as often as possible to double check the distances. And once you're happy with the location, lock the component in place using the lock option in the object pane. Once the larger components are placed, make sure you refer back to the circuit often and try to place the components close to each other to avoid making longer tracks when you start the routing process. It might take a few tries to plan and place the components effectively around your PCB. So once you're satisfied with the layout, we can move on to the routing process. You might have noticed some connection floating across the PCB. These are called rat lines. They represent the connection made in your schematic, but not yet made the connections between the components on your PCB. The process of creating this actual connection on your PCB is called routing. It's quite simple to do in EasyEDA. All you need are these two tools, the track tool and the wire tool. To keep the routing process simple, you can use your schematic diagram as a reference and start routing from one side of the PCB to the another. Now to make the connection, start by selecting your track tool and clicking on a component which you want to start the connection. Here, let me start with the USB-C and the power inputs. Click on a pad where you want to start and another where you want to end the connection. But remember, drawing tracks within your PCB isn't always straightforward, especially when you're dealing with complex or high-speed circuits. There are many guidelines you need to follow to make the routing very effective. So I'll drop a link in the description which will dive deeper into the routing process in more detail, and also an article that will provide some basic outline of the PCB design guidelines. The first track was straightforward to lay out, but what happens when there is no way to connect the track on the same layer? In such cases, we need to use the bottom layer of the PCB to create a jumper connection. This is where the wire tool comes in handy, which helps us in creating a small hole to connect the top layer to the bottom and vice versa. Here's a simple example of how to use wire to make a jumper connection. With the basic guidelines in mind, start routing the rest of your connection. Please take some time and ensure you route everything accurately with proper spacing and thickness, as discussed in the design guidelines. You might notice some extra space on the length since we increased it by 1 mm. You can adjust this back by slowly moving the outline points slightly inward. This should bring us back on track with a size similar to TP4056 but 1 mm larger in width. But that shouldn't be an issue as long as we maintain the correct distance for pinouts like the TP4056 module. You might have noticed that I left out all the ground tracks because we are going to do a ground pour. This will connect all the ground connections together in a larger copper area. While you can complete the circuit just with tracks, a ground pour offers many advantages. It's easier to etch during PCB manufacturing, can act as a heat sink, provides overall circuit stability, and reduces EMI. To create a ground pour, select the copper pour tool and select the copper pour net name to ground. To do the pour, start drawing a polygon around the PCB by clicking at all the 4 corners. Once you complete the polygon, just do a right click and you will see how some of your ground rat nets connections disappear. So let's repeat this process for the bottom layer as well. If you notice any missing connection, like this ground not passing through the small space, you can fix it by adding a wire to both top and the bottom layer of the copper pour. This will make the connection between the top ground plane and the bottom ground plane. If you look closely at TP4056 PCB, you will see several wires on the bottom. These are called stitching wires and they are essential in many circuits for transferring heat from component to the PCB for thermal stability. So let's return to our PCB editor and quickly add this pattern to our circuit using the wire tool. With this, we complete our electrical connection. I usually add names on the silk layer for easier assembly, but since our PCB is compact with little space on the top, let's add text on the bottom layer along with the logo. To do this, select the bottom layer on your PCB and use the text tool, and adjust its layer, content, font and the size in your object pane. For my need, this should be good. Let me finish this PCB off by adding a logo as well. To add a logo to your PCB, use the image tool in the PCB tools panel. In the pop-up, select your preferred logo. In this case, I'm using the PCB Cupid's logo. Adjust these image settings until your logo is a perfect black and white image. Finally, set the dimension for your logo so it fits within the PCB design. Once you're satisfied with all the settings, place the components where you want it and click your mouse left button. If there is a lot more empty space, you can add more information as well. So let's quickly add the PCB Cupid's website. This wraps up our PCB design using EasyEDA. If you like to see a quick 2D image of your PCB without this layer clutter, simply click on the 2D icon in the toolbar. And similarly, if you like to view your PCB in 3D format, click on the 3D icon. This will display a stunning 3D model complete with all the components used on your PCB. We have successfully built a fantastic PCB using EasyEDA. But before we can send it for manufacturing, there are a few more steps to take. In this video, we'll see the steps for using DRC to identify and correct design errors and generate a Gerber file that can be used by any fabrication plant around the world. Design rule checking or DRC is an essential part of PCB development. If you have watched our KiCad videos, you will know that we have set up the design rules before we even started designing the PCB. However, EasyEDA is a bit different. Its default design rules are configured to suit many popular manufacturers. So if you have followed the generic design guidelines for most of your routing and placement, you should have very few to no errors while running the DRC. Let's see how many errors we encounter for this particular circuit. Go to the toolbar and click on DRC. EasyEDA will then check for any mistakes made during the PCB design process and display the results in the right pane. As you can see, no errors are currently shown up here for me, but that might not be the case for you. So let me first show where the design rules are set and why are they set that way. Then we'll look at how to fix those errors that we might face if we make changes to the design rules. To view the predefined design rule, go to the design drop-down on the toolbar and click on design rules. This will open up a pop-up with the default design rules and all the connections where these rules are applied. The values here might seem little arbitrary, but they are determined by PCB fabrication plant and their capability to produce PCBs. Since EasyEDA is owned by JLC PCB, we can check their capability list on their official site. First, let's look at the minimum trace width, which is 0.127 mm. If we cross-reference this with the EasyEDA, we have more clearance than required, that is 0.254 mm, which is excellent. Just because JLC PCB supports 0.127 mm doesn't mean every other manufacturer out there can handle the same clearance value. So it's better to set the clearance value a little higher than required. Similarly, if I compare the value for total clearance, wire diameter and wire drill diameter, everything stands at a good value and more than the minimum requirement, which is excellent. Now if we go back to the design rule, we have an option called track length. This isn't something defined by a fabrication house, rather it's a track length that we need to set for our tracks. Most of us won't be using these settings until and unless we start using impedance matching. So for now, let's not worry about this. So far, this default design rules have been applied to all the tracks on the circuit. But there might be a situation where you want different design rules for different tracks and connections. Luckily, we can do that as well. Just click on the add button here to create a new empty rule. Let's start by giving it a name. I'm going to call it power. So I can use this design rule for all the power tracks. Then let's set a minimum track width, clearance value, wire diameter and wire drill diameter. I know it seems like I'm rushing through all these design rules right now, but don't worry. We have a dedicated video related to design rules in our KiCad series. So make sure to you watch that video. Even though it might not be related to EasyEDA directly, all the design rules and application will remain the same. We have added a new design rule called power, but this rule hasn't been applied to any of our connections yet. To apply this rule to the connection, go to the scroll window and select the connection name that you'd like to change. Since I named it power, let me use the VCC connection as an example of how to apply this rule. Here under set rule dropdown, select power and hit apply. This will apply the power rule to the VCC connections. I hope this video has helped you understand the design rules and how to create custom ones for your PCB within EasyEDA. So if you think the video was worth watching so long, please make sure you give it a sub. Anyway, now to test this new rule, simply click on settings and run the DRC. You'll notice a lot of errors popping up just by adding a single additional rule. Fixing these errors without disrupting the layout or routing can be challenging. So for now, I'll remove this additional design rule as our circuit is very simple and we don't have to make it complicated with this additional rule. However, I'll still show you how to fix the errors that can occur during DRC. I'll keep the changes I made to the default design rule and hit the settings button at the bottom. Now when I run the DRC again, we have a few errors. Two of them are related to the spacing between the track and the pad, and the other one is related to track and a wire. And the best part is EasyEDA shows the minimum spacing that it should be and what is the current spacing, so you can fix them. Just for demonstration purpose, instead of rerouting or adjusting the track, I'll simply reduce the track width from 0.5 mm to 0.3 mm, and you can see the error is automatically fixed. Now let me do that for other tracks as well. One important thing to remember when reworking tracks that already have a copper pore is that you need to rebuild the copper area after each change you make. So the copper pore is updated with the latest changes. Now after tinkering with it for a while, I was able to eliminate all the errors, which makes our board ready for manufacturing. The best part about using EasyEDA is how easy it is to place an order for manufacturing your design. Just click on the Gerber fabrication icon. This not only allows you to generate a Gerber file, but also gives you a cost estimation for manufacturing your PCB. You can play around with this and see how changing the color of your solder mask, quantity of PCBs affects the cost. But let's say not everybody wants to manufacture their PCB from JLC PCB. In that case, you can just click on Generate Gerber and it will download a Gerber file which you can send for other manufacturers. And this brings us to the end of the video. If you enjoy content like this about PCBs, make sure to subscribe to our channel. And if you have any questions or doubts related to PCB, drop them in our PCB Cupid Q&A section. Until then, keep learning and keep creating.